Any questions? So we're at a turning point. We're basically halfway through. We've done most of the theory, at least as regards absorption and emission. I want to turn now to some applications in which we're going to use, show you examples of tunable diode laser absorption. These diode lasers mostly in the visible into the infrared. So mostly we're talking about infrared low vibrational transitions. With one exception, we actually can measure oxygen in a low vibronic band, importantly. We'll show that too. So the spectroscopy will look like it's simple now because we're making use of known spectra, simpler spectra. We're avoiding the complexities that we just went through, mostly. Talk about the history, really. I've been working with diode lasers for a long time, and so I can tell you something about the history of how it's evolved and how important it's become for aero propulsion especially. There's a couple of different strategies we'll talk about, some general information about lasers and detectors, and then some applications down here and some trends. This is a picture of an experiment we did at the University of Virginia a few years back. They have there a continuous direct connect scramjet combustor flowing upward here. There's the exhaust. We wanted to make some measurements in this high temperature region here to go along with computational modeling and validation of those computational models. Example application. Okay, I've been working on diode lasers a long time. I was supported by the Air Force, and the monitor retired, and we did a tribute to him. And one of the elements was to point out that over 35 years, we'd gone from an initial idea all the way to a flight experiment that he could take some credit for. So it was around about 40 years ago that I started doing this diode laser absorption in shock tubes, flows, flames. My first paper was probably around 1977 or so. These are just highlights I'm going to give you. But another 12 years later, we learned we could measure the mass flux of oxygen corresponding to the inlet of an airplane using diode laser idea. So not measuring species, but measuring a combination of species density and velocity. A little bit later, we went to Calspan, now called Kubrick, in Buffalo, New York, where they have a hypersonic tunnel, shock tunnel, which produced Mach 16 flows, and we showed that we could make measurements in a Mach 16 flow to help characterize the performance of that tunnel. We learned how to do combustion control by measuring absorption of light and controlling the dynamics of the combustor. It became easier now by around 2000, to start measuring multiple things at once. These were some important target species. I would say the last 20 years or so, increasingly these methods are used to characterize the flow facilities, typically difficult flow facilities, arches, hypersonic tunnels, gas turbine sector rigs, and so on. So where you're trying to understand how is this system performing. In some cases, you're actually trying to get quantitative data for comparison with computational models. So I'll call that engine testing, scramjets, aircraft engines, IC engines, detonation engines. So all of these things we've studied all of them. Here's an example at the Wright-Patterson Air Force Base in Ohio. Greg Grieger now at Colorado, ground test rig for scramjets. So these diode laser techniques I'm going to tell you about have evolved from an early start over a long time now, 40 years, to be very powerful tools based on the spectroscopy I've been telling you about, but a simplified version because usually in the infrared, you're just making use of tables of tabulated line positions. Finally, in around 2012, they actually flew this diode laser sensor on a so-called high-fire scramjet flight test conducted in Australia using an 8-diode laser line-of-sight combustor idea. Of course, it's a lot harder to do these things in flight than it is in a laboratory, but that's one reason why it took so long. So this is to let you know that there's a lot of potential applications of what I'm telling you about. About 20 years ago or so, I had this idea that we should be able to convince the Air Force to sponsor research in which we would probe different places in this simulated scramjet here. We would take a family of diode lasers of different colors, wavelengths, propagate them by fiber, and we would use them to interrogate different parts of this scramjet combustor. looking at the inlet, looking at the combustor, looking at the exhaust, measuring a variety of different parameters that are relevant. Propulsion people want to know how much fuel is going in, how much air is going in, and how much thrust is produced. So we learned over time to measure temperature, velocity, water, CO2, O2, and other species. We would test those ideas on various test rigs at Stanford, and then they would be transferred to some ground test facility somewhere, and then eventually, I think, we'll see these things in flight. So back to some fundamentals, but kind of a simplified form of fundamentals now. What we're talking about is taking a laser source, usually a continuous wave or CW laser source, operating at some frequency nu or wavelength lambda, incident intensity I0, propagating it across the duct path length L and measuring the fraction of the transmitted light, where tau is the fractional transmission. So that's the ratio of the output transmission light to the input light, neglecting the windows. We assume usually that it's uniform along this path, and that's a deficiency in the theory, but that's what we have to do. So now we imagine we scan across an individual feature that we've picked out. So we picked a line free of interference that's going to tell us something. We scan the laser across that line, and that would be called scanned wavelength, line of sight, direct absorption. We call that scanned DA. We impose the Beer-Lambert law, which applies to monochromatic light, in which that fractional transmission is given by our K nu L. Or if the molecules are big, we'll sometimes write it as N sigma L, where K is replaced by a cross-section and a number density. Here, the number density is buried inside K. In this case, I'll write it out in the form we usually use, which is the product of the line strength, the line shape, the mole fraction, and the pressure. So that's because we're using units of centimeters to the -2 per atmosphere here. Pressure in atmosphere, mole fraction, and there's the line shape function that depends on temperature, pressure, and also on the composition. So now, if we're interested in velocity, we might take some of this light and pass it through at an angle, compared with the light that goes perpendicular to the flow. This beam would be Doppler, would not have a Doppler shift. This beam would have a Doppler shift. So when we scan the laser, these two different detectors would show the line appearing at different places. That separation being the Doppler shift, which is the average component of the velocity along the laser. You need to have two components to get the total vector. My idea is that the shifts, which we get for the velocity, the shifts and the shape contain useful information. So if we can measure the shape and the shift, we can get what we need. Temperature is really important in reacting flows, and so we frequently want temperature, and the best way to get temperature is by scanning two lasers, one laser or two, across two lines of the same species. So if it's the same species, the ratio of the absorption, either the area under the curve, which would be the line strength basically, the ratio of those line strengths would be a function of temperature alone. So we get the best way to get temperature is from the ratio of absorption at two wavelengths for the same species. Well, once you start learning how to do this, you say, well, why don't we use 3 lasers? Why don't we use 4 lasers? Why don't we use 5 lasers? We call that wavelength multiplexing. So you can begin to look simultaneously at multiple wavelengths or colors, which you might use to measure multiple species, or you might use it to begin to attack the non-uniformity along this line. What if the composition or the conditions are varying along that line? How do you figure that out? Well, you can do that by using different wavelengths of light with different sensitivities, and that can be done. Not easily, but it can be done. There's 2 ways that we primarily execute these diagnostics. The first one is the scan DA. So in this case here, you have a compact little diode laser, whose temperature is usually controlled with a thermoelectric cooler. And you vary the wavelength of light that comes out by using typically a sawtooth of current. Sawtooth of current drives this diode to emit light of changing colors. It also happens to cause it to change intensity. So typically when you do this scan, this is now intensity. You get an intensity that ramps up simultaneously with wavelength change. Here's the absorption feature that we're after. So you typically fit this baseline, the baseline fit for the I0, and then you take the local value of I, take I over I0, take the negative logarithm and replot it as the absorbance. That's what we're after. We're after this plot of absorbance. In this case here, the peak absorbance is about 0.75, so we're looking at significant absorption. Okay, that's what we would like to do, and that's called scanned DA. And that's the method that is preferred if the absorption is strong enough that you can easily discriminate it against this background sloping line. On the other hand, there's times when absorption is not strong enough and we resort to something called wavelength modulation. So now we superpose on this sawtooth a high-frequency sine wave. It means that the light coming out is oscillating in wavelength narrowly about a center frequency as we scan. So we're seeing an intensity increase like we do here, but we're simultaneously seeing oscillations up and down as we play with as we're changing the wavelength. So that means at any one time there's a specific wavelength, but the wavelength is modulated rapidly at a frequency f. So typically we take that signal and we pass it into a lock-in amplifier, and we will ask for the signal at the modulation frequency f and the 2f. Roughly, the way to think about this is that the 2f signal is the second derivative along this curve. So basically, second derivative is 0 out here, and then here's the second derivative. So that's basically what we're doing. However, if you take that 2f signal and you divide it by the 1f signal, which is essentially the slope, you remove the dependence of that signal on the intensity. That turns out to be a big advantage. So we call this wavelength modulation spectroscopy. It has the virtue that the signal in the wings of a line is nominally 0. It's always better to look for the deviation from 0 than the deviation from a varying number. So WMS also allows us to reject noise because we do all the signal processing at high frequencies. So we basically can exclude all the stuff that's happening at low frequencies. So these modulation frequencies tend to be high. So that WMS, wavelength modulation spectroscopy, improves our noise rejection, allows us to detect smaller absorptions. 2f over 1f method also, because it's independent of the intensity, cancels any scattering losses that might be present. So if you have particles in the flow or contamination in the flow or windows that are getting dirty with time, the scheme cancels all of that out. So I like to say that WMS, students don't always agree with me. I say it can be 20 times more sensitive, but it's also probably 20 times more complicated electronics that are involved. So I always favor myself, scan DA if the signal's big enough. It's almost foolproof. Normalized WMS has big advantages if you need them. This is an example of how well this works. So here's a case where we have a modulated TDL at 1392 nanometers. That's the place where water vapor absorbs strongly. So we pass this across some path in the room, pass this light from the laser onto our detector, about a foot, 38 centimeters. And there's about 6% absorbance due to water vapor in our room, 60% relative humidity, 296. We get about 6% absorption over a path length of 30 centimeters. So it's sitting there. Now, if we gradually introduce a knife here, a knife edge, and block some of the beam, here's the 2F signal. Here's also the 1F signal. Both of them go down because there's less light reaching the detector. If I take the ratio of those two signals, it's now the constant. So what that's telling me is that this idea works, that the 2F over 1F nulls out changes in scattering losses or beam blockage. That's if we use a kind of slowly varying knife edge. You can do the same thing by pounding on the table with a hammer. Look at these fluctuations that occur because of the misalignment that's induced by the vibrating optics. Causes less light to reach this detector when that is occurring. But again, when you do the normalization, it goes away. So this is a clear demonstration that the 2F over 1F method, where we're measuring, in this case, water vapor over 1 foot, solves the problem. It has some advantages in terms of signal-to-noise ratio, absorption, detection limits, but also in terms of dealing with vibration and dirty windows. Especially when you go into the field, you make a campaign on a combustor, coal gasifier, a scramjet, anything that's got windows, and it's vibrating and it's noisy and it's hot and dirty, window fouling becomes a big problem, or particulate scattering from soot or particles. So this concept solves that problem, minimizes it anyway. So you might ask, well, gee, this looks pretty good. What species and wavelengths can we deal with here? Well, let's look at the combustion species. So nitric oxide, this is wavelength now out to 6 microns. The vertical axis are the line strengths or the absorbances for fixed temperature, pressure, mole fraction, and length. So basically your fixed conditions. And these are the absorbances. Now what you'll see is that, well, there's a weak NO, stronger NO, stronger NO. Here you can see okay, so which side is this? Longer wavelength. That's a band. That's the 0, 0. That's the fundamental band, 0 to 1. Now you know enough to say, well, gee, I know that longer wavelength is shorter energy. That must be the P branch. And this must be the R branch. And it looks like we might be starting to see a band head here. I'm not quite sure what that is. If we look at carbon monoxide, this is the fundamental. Remember fundamental, delta V of 1. First overtone, delta V of 2. Second overtone, delta V of 3. If it had been a harmonic oscillator, these are 0. It's not exactly harmonic. It's pretty harmonic. And that's for that reason, this absorbance is 100 times this absorbance. So by going from the second overtone to and the reason I'm going this way is that over time, the lasers have moved this way. Originally, the lasers were built for telecom people and visible. Over time, people have learned how to make lasers at longer and longer wavelength, which means smaller and smaller photon energies, bigger problem for material scientists. But now we can work right here. It's 100 times better than working here. If you need that factor of 100, you can get it that way. CO2 is the same thing. There's a gradually increasing strength. So you'd like to be out here. I think I showed this before. The good news about water is that water is absorbed everywhere, and the bad news is that water absorbs everywhere. So you have to kind of search for windows through the water vapor if you have water vapor present. We do a lot of work with hydrocarbon fuels. And here's an example with endodecane. That's C12H26, I guess. It has an absorption around 3 microns that's associated with the so-called CH stretch of that molecule. So these are some species we would care about. And these are some wavelengths that we can readily access. When the molecules are small, and these are all small, they have discrete structure. So even though this looks like a continuous distribution here, there's windows in between these lines that we can understand. So each of those lines is a position we can calculate, or we can decide which line we want to use. So you might say, we want to measure NO. It's around 700 degrees. What transition should we use? Well, you want to use one that's near the peak, if you need to have strong absorption. And you want to pick one that's free of interference from CO2, from CO2 and water. So you have to search around in the available wavelength range of your laser to find the best transition, where it's and the strongest. Large molecules we have to deal with a different way. They have blended features, and we tend to do that with some different strategies than I've showed you. Well, where can we buy lasers? I've drawn a barrier here between what I call mature and emerging, but actually this barrier just kind of keeps moving across. Mature means that basically means you can buy them and they're cheaper. Emerging means there's not so many available, you're going to pay more money. Each of these different lasers has some different geometry. They have different names. We have quantum cascade lasers, integrated IC lasers. So there's different material science structures needed to access these longer wavelengths. We would call this the visible. We would call this the near infrared, out to about 2 microns. We'd call this 2 to 3. We'd call this the extended near infrared. And we call the mid infrared kind of here, out to about here. Those are very loose names. So mostly we would like to work in the mid infrared, where these lasers are available at variable cost. So here's some species that we've worked with over time. Hydrocarbons. There's a lot of atoms that we could be working with, but we're not down here. We're not pursuing that right now. So these lasers provide access to many atoms and molecules. When I started it 40 years ago, it was really hard to get a laser that would work over an even narrow range. We worked a little bit right here. Now, another nice thing about these lasers, they can be fiber coupled, so you can have some sort of a fiber coupled. The laser's here is small nickel or quarter. And the light can be propagated by fiber to your experiment, so you can keep the laser in a nice, safe spot. This is an old slide, but these basically driven initially by the telecom industry. They were available at a lot of wavelengths. Nowadays, these are really scientific applications here. You might pay $40,000 for a laser out here. You might pay tens of dollars. We're buying some lasers right now down here that are, I think, around $10. Okay, now what about the lasers and the detectors? So the lasers might look, these diode lasers, strictly speaking, they're not all diode lasers, but it's a kind of a loose terminology. We call them diode lasers. These lasers might, I said here, 1,000. In the near to extended infrared, they might be in the $1,000 range. They can be fiber coupled out to about 2.5 microns. Beyond the 2.5 microns, we don't have good fibers that transmit infrared light, but they're emerging. We go out to the extended, into the mid-IR, we might have to go with what's called a quantum cascade laser. Not strictly speaking a diode laser. We might pay $40,000. The power levels tend to be in the range of, say, 1 to 500 milliwatts. You buy these things from around 400 nanometers out. As you go out in wavelength, the photon energies are smaller, and it becomes a material science problem how to do this. So low power is fine for, I should really say, is fine for low power for absorption experiments. It's frequently not enough to do fluorescence. Lasers tend to be pretty compact and rugged, good lifetime. They can be tuned over multiple wave numbers by changing the current or the temperature. Usually you fix the temperature and you ramp the current. The newest external cavity, that's the geometry. These newest external cavity lasers can be tuned about 100 wave numbers. What kind of detectors do we use? Well, the wavelength you use dictates the detector that you use. The detectors tend to be what are called quantum detectors. That is, they respond to individual photons. So they're designed with material properties such that they can respond to the energy of the photon. The photon is in the kind of the 0.2 to 1 micron range. You could use silicon and so on. So each of these detectors, indium arsenide, indium antimonide, cooled indium antimonide, mercad telluride, they respond in different wavelength ranges, and they have variable costs, and they have also variable speed. So depending upon the wavelength down here, you have some choices of different types of detectors you can use. So if you want to work out here at these longer wavelengths, we tend to be using these lasers called mercury, cadmium, telluride, mercad telluride. You can use photomultipliers for high sensitivity detection out to a micron or so. And now these detectors come with different speeds or bandwidths. And so if you're looking at fast transients, you need fast response, you need high bandwidth. Here's a megahertz. So you can get megahertz detection, but if you want to get tens of megahertz or 100 megahertz, now you have to be very careful to get detectors that are designed to give you high speed. You can get indium, gallium arsenide detectors that are pretty fast. They have to be really small. So you have to pay attention to the laser and the detector to do these experiments. Sometimes the detectors are characterized by something called D star. It's a parameter that tells you something about the signal, the noise level of that detector. It's a normalized thing, which basically the square root of the area and the bandwidth and the noise equivalent power. So what you'd like to have is a small noise equivalent power. You'd like to say that from my detector, I can detect a small amount of power. So what's the noise level? So you want that number to be small. Usually this is done so you buy a detector that's got a good D star. And you have to be sure that it's got an area that allows you to have the bandwidth. Usually the bandwidth goes up as the detector gets smaller. Usually you want the detector to be bigger so you can capture all the light. So it's kind of a trade-off there. But anyway, you have to think about the detector to be sure that it's efficient and fast enough at the wavelength that you're going to work. Of course, you have to decide, well, what time response do I need? Am I measuring drifts over seconds, or am I measuring changes over nanoseconds? You have to decide. If you try to make measurements at high speed, you're going to pay a price in noise. So you don't want to pay that price unless you need to. Okay, I want to give you some example applications. In near infrared region, we started really in the visible, worked into the in near infrared, extended near infrared, gradually into the mid infrared. But there's a lot of CO2 in, it's relatively inert, a lot of CO2 in combustion, and there's a lot of good transitions to use near 2.7 microns. So for years we worked on how can we measure temperature really accurately using our line ratio ideas with CO2. And I'm going to show you how well we finally got that done. Here's the spectrum for CO2 out to about 3 microns. All of a sudden, now what are these things? Remember I told you about combination bands. What is that? These are transitions in which 3 quantum numbers change. The new one mode changes by 1 quantum, 2 quantum, 1 quantum. Reasons we don't want to go into. There was a blend of lines here that fall into the overall energy change corresponds to 2 microns. So that's, but here's the strength over here. So but if we got to 2.7, it looks like we're 50 times stronger. And this is some sort of blend of the new 1 plus new 3 and the 2 new 2 plus. All of this is known. It's, you can look it up in high trend. Positions of the lines and their identification is all in high trend. Those numbers, they would give you the line positions of these lines and the strength at a specific temperature. But now I want it at 1200, so now you're going to have to take what is in high trend at 296 Kelvin and convert it. There's a lot of opportunity here for different line pairs. So we worked in this region. We picked out some lines. Looks like this, looks like a mess, but if you blow it up and sort through it, you can find there's a region here in which you have at least in this narrow range between 3633, 3646, there's quite a few individual lines. This is the R28 line. So that means that we have a delta J of 1 with J double prime of 28, starting from the ground level, vibrational levels, to the quantum changes of that particular band here. I don't know whether that's the new 1 plus new 3 or this one here. This is the lower state quantum number. This is the relative strength at 2 temperatures now, at 650 and 1200. At 650, it's here. At 1200, it's way down here. So that transition is very temperature sensitive. Good. However, we want to take ratios. I think I'm going to have to start using my other pointer. We're probably going to pick this one here. This is the P70. 70 is a big number. What does that mean? Populations are a lot less than they are for 28. I might take the ratio of absorption between these 2 lines as a good place to work. So we selected that line pair. It turns out to be isolated from water, and it has a wide separation in the energy level, which we need for temperature sensitivity. And we're going to show how well this works in a shock tube. So here's a shock tube experiment where we have a shock tube with an end wall. Here comes the shock wave. It's going to heat that gas. The reflected shock goes back and leaves behind a stagnant sample. And we're going to send in our diode laser, send it across, and go onto the detector. And we're going to see how well we can measure temperature. We're going to, after a few years, we decided to use the WMS method. It has an advantage. So we went to the WMS method, and now we have to have 2 colors. We have a laser at 2.743 microns and 2.75 microns. Each one is being modulated across an individual line. So these 2 paths cross at the same axial location. We send these to the data acquisition system. They're being modulated at 100 kilohertz. And this data acquisition system will give us the output signals, which we can use to try to get temperature. Now you might say, well, how good is your choice of lines? Here's the ratio. Here's the 2F ratio as a function of temperature for these 2 lines. 2 different pressures, so it's kind of independent of pressure. And what you want is the steepest slope you can get. so that you get the maximum change in the ratio per unit change in temperature. So it's been optimized. Now I'm going to show you how well this works. So this is an experiment in which we have about, in the test gas condition, about 1 atmosphere, 2% of CO2 and argon. And this is now plotted versus time. And this blue is the pressure. So what we see at our measurement location, which is 2 centimeters from the end wall, we see the arrival of the incident shock wave and then the arrival of the reflected shock wave, and then we see a constant pressure. So for about 9 milliseconds, we have a constant temperature and pressure environment to test our sensor. And as long as that's nice and flat, we've done everything right, we know the temperature quite well. And here's their ratio. Here's the temperature we get from our sensor. It's flat, just like it should be, and then it tails down as it should. Now, if I blow this up and say, well, how well did I do this? Here's the difference between the signal versus time. This is the difference of the measurement and the calculated T5, it's called. The calculated T5 is a constant. So these are the fluctuations. So basically, this is the best experiment we've ever done. We had a precision of about 3%, 3 degrees Kelvin. I don't think anybody's ever get close to this. Even my current students haven't got back down to this level. So we try to measure temperatures to 5 degrees. And of course, we've assumed that it's uniform. We've made some assumptions. But that's a pretty accurate, precise temperature measurement. We can now take that. And because we've used the WMS method, 2F over 1F, we can apply this to a multi-phase flow. I'm going to show you that example. So this is a case now where we have, again, we still have 2% CO2 and argon. But now we have an endodecane aerosol. So we have a fuel aerosol. A shock tube is filled with an aerosol of fuel, meaning small droplets. Now we're going to plot the extinction of the light as it passes through the droplet cloud. So here's this extinction. So the extinction initially, here's the shock wave, incident shock wave. The extinction was around 0.25. About 25% of the light's blocked by the droplets. There's no real vapor, not much vapor at that point. We don't care anyway because we're measuring CO2, not dodecane vapor. So this is the extinction of the light. The extinction increases after the compression of the incident shock wave, and then the extinction drops to 0. Why does the extinction go to 0? The droplets evaporated. The blue signal is the measurement of the droplet loading in size versus time. Here's the initial droplet loading. They're compressed by the density jump across the incident shock wave, and then the extinction goes to 0. This is the return of the reflected shock wave. The extinction is 0 because there's no longer any droplets. Now, what about the temperature? The temperature we get from the CO2. I don't remember what wavelength we used for this droplet extinction here. It might have been a visible color. Now here's the temperature we measure with our temperature sensor. It starts down here at 300. Incident shock comes along, it jumps up to about 540 degrees. And then the temperature declines down to this final value. And then it jumps back up to the post-reflected shock value. Why does the temperature decline? Answer, droplet evaporation. So we were able to measure the temperature of the gas in the presence of droplets that are evaporating. That's the power of this idea, of being able to work in a droplet-laden or particle-laden flow. Successfully measures temperature in the presence of an aerosol. Okay, that was my combustion example. I want to move to some aerospace applications. We're interested in measuring velocity, first in our laboratory wind tunnel, and then we tried to measure it in a test facility at NASA Langley in an initiated combustor used to provide inflow for a Scramjet module. And I'll show you some work from the University of Virginia. The first case here, we were measuring did this with oxygen and we did it with water. The geometry is the same. So basically you take the lasers, and we would take two typically, and we would then put them through the flow at two angles. And so this beam here would be going against the flow. This beam is going with the flow, so they'll have different Doppler shifts. And the spacing between the lines we observe would be twice the shift for either beam. And by doing that, you don't have to measure the absolute Doppler, the absolute frequencies, you just measure the delta. This was based, initially we did this for oxygen, but then we moved on and we did it with water. We did this in preparation of going to NASA Langley to do it in their facility. We get the velocity from the Doppler shift of absorption. We do this in a subsonic wind tunnel, so we know the actual velocity, and we can ask how good it is. Here's the work we did. This is now velocity measured in meters per second. Here's our Doppler shift value. Excuse me, this is the measured velocity and this is the tunnel velocity. So everything should fall on the straight line. So the important point is that we're able to measure the velocity by the Doppler shift all the way down to, well, I think that's a false point. I think we only got down to 2 meters per second. The same concept that I used to show you that we measured 14 kilometers per second. Day one, I guess. So we get really high precision when we do this carefully. I'll take you to NASA Langley. Now they have big test rigs at NASA Langley. So they want to take air and they want to put high speed. They want high speed air to go through this combustor. They want to test the performance of the Scramjet combustor. All of this is to prepare the air to go into the combustor where they're going to have some fuel injection. This is called the isolator. So upstream, how do you get high-speed air? So you can compress it and then you expand it, but if you expand it, it's cold, and they don't want it to be cold, so they heat it, and that's called vitiation. So they do some heating of the air so that when it enters this region here, this isolator where it calms down, it'll have the inlet conditions they want to study this combustor to simulate hypersonic flight. Question is, how do you know exactly what's coming into this test rig? They designed this nozzle for when we were there. They designed it to produce a static temperature of 1,000 degrees, 0.7 atmospheres, and this would simulate the entrance condition for a combustor for a scramjet flying at Mach 5. So the nozzle, it simulates Mach 5 flight. That's the point. So we built, I should say the student built, he built translation stages so that he could probe this system here, which is rectangular. Here's the geometry right here. Probe it by scanning his laser beams upward or sideways. So he has two different kind of translation stages he could use. So we had to scan the laser beams to map out this test section. The goal was to measure the velocity, the temperature, and the mass flux. How can we do that? Well, we can measure the velocity by the Doppler shift. We can measure the temperature from the line ratio of the water vapor lines, and we get the mass flux by if we know something about the concentration of the water in the air. So this is a sideways view with the system, the translating sensor in place. Here's it's coming into this isolator section before it enters the combustor here. This is our apparatus right here. This is the scan. This is just a schematic of how we would scan horizontally and vertically over the 7 by 13 cross section, so that we can. Now our measurements are going to be in a plane, and they're going to be path integral values that we have to think about. So in the vertical scan, this is now the vertical direction, very over 7 centimeters, I guess. This was our. I'm just going to show you the velocity data. These are the velocity data that we got as a function of vertical coordinate. And Blue was the CFD past average simulation. So basically, we were able to pick up not only the values right in here, but also in the boundary layers. That was pretty good. And because the sensor is pretty fast, we could actually observe transients. So here's a case where we predicted a velocity of 1,630 meters per second. It was their test condition. But you can watch the tunnel turn on, oscillate a little bit, behaves well, and then turns off. So they just run this thing like 20 seconds to simplify any cooling requirement. I'm just showing you the velocity part. So from these data, we got temperature, velocity, mass flux to validate the performance that they thought that this tunnel was running. So they use CFD together with some quantities like the various pressures and mixtures to calculate the performance. Okay, now we went to a test rig at the University of Virginia, and we were working in there. Now this is an electrically heated test facility, much smaller. Because it runs continuously, there's water vapor, there's water lines everywhere, windows on the sides, and the flow is going this way, and what this is off to the side is a cavity. The flow has a fusion here, and that's the cavity that stabilizes the flame that allows these supersonic gases to burn. So somewhere here they inject fuel. Here's high-speed, high-temperature air. Fuel is injected. There's some recirculation, and that causes stabilization of this Mach. Now this is it's Mach 5 flight condition corresponds to Mach 2 here. So that was this was the ethylene air experiment, equivalence ratio of 0.15. Very noisy. So people are outside. You have to be outside of the room because it's a little bit dangerous. So we're outside of the room. Everything's done with fibers and translating lines of sight. And so we were able to probe along different lines of sight. We translate here, and we can do this both in the here's the cavity right here. Measurements here, then we made some measurements at the exit of the cavity. And the idea was to make measurements that could be compared with CFD. How do you validate the CFD? So we were doing this with fiber-coupled mid-infrared. There were also some people there using planar laser-reduced fluorescence of OH. I'll be talking about that later in the sequence. Making measurements here. Basically, we measure temperature. It's a path integral, but we're using two different transitions, 0 and 20. We use CO lines of 6 kilohertz. Here's this was the V equals 0, J of 20. V equals 1, J of 14. And from that, you can get the temperature. Now, this is mostly noise, I would say, 140 degree. We're about 1,600 Kelvin. We're able to do this. And so there's information content in the mean and also the information content in the fluctuations. What was interesting is if we compared the simulated in the red points, were simulated conditions as a function of distance from the wall in this cavity. We got good agreement with CO2, not so good agreement with CO. So some of that's a big enough difference that it's not the experimental error. There's something about the flow in that cavity that's not behaving the way that they wanted it to. CFD overpredicts the CO in the cavity. I had a student who went to Wright-Patterson Air Force Base. He's now a professor at Colorado, Greg Rieker. So you get a size of this feeling for the scale of this experiment. So this is now a continuous experiment. So you see water vapor, water cooling lines everywhere. You see the scale of this thing. So when it's big like this, they're testing a larger scale test engine. He did this about 10 years ago. And the question in this scramjet, one of the questions in the scramjet combustor was, what are the conditions at certain axial locations? And also, under what conditions does the engine unstart? At what conditions does the flow choke and the combustion exits the cavity? That's not good. So in this case, we did was, so let's measure 4 water vapor lines. So we got 4 colors here. Chosen such that 2 of those are going to give us are good at high temperatures. And 2 of them are good at low temperatures. And we take that light, pass it across the combustor. and we distribute it over on some detectors. And we're going to do wavelength modulation. And here's the inlet flow. And the question is, what's happening? What does the combustor produce as before the exhaust? So we're going to measure 4 water lengths, and we're going to infer really 2 values of temperature. We're going to infer as a function of time in seconds the temperature we get when we use the ratio from the high-lying line sensitive to T, and the temperature we get from the low line. So if the flow is uniform, the temperature is the same everywhere. And it is for about 30 seconds. And at about 30 seconds, what we find is these 2 data traces begin to diverge. So that's telling us that the temperature is non-uniform along the line of sight. Well, we can learn that, but we'd like to know more. We'd like to know what's going on. And so we got clever, and we said, let's do a running Fourier transform and look now at the frequency content of the signals. Because if you look close, you see that in the green, the frequency fluctuations are different than in the blue. There's something going on that's different in the low temperatures. So we look at ratios of frequencies. Look at the ratio of the frequencies, and we find, sure enough, that when the engine is running stable, the ratio of these fluctuation frequencies is constant. But when it goes unstable, we begin to see this. So what is this? This is an example of how you can look at low frequency fluctuations to anticipate poor performance of this combustor, which is called inlet unstart. Fluctuation sensing. For us at the time, that was the new paradigm for control, using fluctuations rather than absolute values. We also use this as a basis for control of another combustor. What are the future trends? How am I doing in time? Good. What's happened over the 40 years or so we've been doing this is that lasers are more available, more species can be measured, we can do things more accurately, and the systems are becoming cheaper and they're becoming more portable. So we've now taken these portable diode laser-based sensors to a variety of places, from New York to Ohio to southeast of the country. And so I think what we're going to find is that these will become engineering tools, not just laboratory curiosities. But we can do this in energy systems too. It's not just in aerospace. It could be routine. It could be used for looking for maintenance. For example, I argued to NASA Ames we should use this to measure the erosion of their copper electrodes in their arc jets. Just sit there and tell them what's happening. Or you might eventually use this in research flight systems where you're trying to understand performance. Maybe you could detect some sort of malperformance in the combustor system. Or maybe you could optimize fuel flows or something that you'd like to do by looking at species, temperature, velocities, and fluctuations. Gradually over time, we've learned to extend these ideas into the ultraviolet and further into the mid-IR, stronger transitions, everything gets simpler. Right now, we're spending a lot of time with hydrocarbon species. Spending a lot of time with hydrocarbons we detect out at around 9, 10, 11, 12 microns. Sometimes we worry about pollutants, NO and NO2, worry about combustion control, combustor efficiencies. Gradually, I think we can continue to do research, but I think we'll see these tools being used more and more by the engineers in the facilities. Did I show you? There's an upcoming thing. I see Professor Reese in the audience. So I should show him. Well, he probably knows. He's got one of my students in his group. But we've learned how to make measurements in IC engines that are pretty sophisticated. So I'm going to show you about IC engines, fuel and temperature, flagging coal gasifier, emissions of and these are full-scale combustors. Student here is 100 feet up in the air. So what does that mean? We've learned how to do this in a laboratory. We take it to a real system. So absorption has the benefit of being portable, economical, sensitive to a lot of species. What's the problem? Well, you do have to know something about spectroscopy, unless it's a packaged instrument. And you have to live with the fact that it's a path integral number. So if you're trying to study turbulent combustion, this is not the tool you're going to use. But if you want to know the path integral of NO emissions from your combustor, it's a great tool. So it's either a plus or a minus, depending on your point of view. Okay, I think I'll stop there, and we're through a few minutes early. Any questions? So my hope in this last hour is you see all that stuff we went through in theory has application. And when you finally get to the application, you're narrowing in on a particular question, and you don't